So here's the end of chapter 3, calculations with balanced chemical equations. So we learned how to write chemical equations and balance them, and now we're going to use them to do stuff. When we look at a balanced chemical equation like this one here, 2CO plus O2 produces 2CO2. We can interpret these coefficients in different ways. We can interpret them to be numbers of molecules or atoms, right? And that's what this picture is showing. 2 carbon monoxide molecules react with 1 oxygen molecule to produce 2 molecules of carbon dioxide. So we can write that. Right? So 2 of those molecules and 1 of those molecules makes 2 of those molecules. We could also multiply that by 12 and say that we have 2 dozen carbon monoxide molecules would react with 1 dozen oxygen molecules, and how many dozen carbon dioxide molecules would that make? 2 dozen. Or instead of using regular dozens, we could use the chemist's dozen, which is a mole, right? So we could interpret that to mean 2 moles, 2 times Avogadro's number of these carbon monoxide molecules are going to react with 1 mole. Yes?
So are you just increasing the amount, but like within the same proportions?
Yes. We're increasing the amount, but it's the same proportions, and it's based on numbers of particles. Okay? 1 molecule, 2 molecules, that's extremely small scale, right? That's never going to happen in anything that we're doing because you couldn't even see that. So when we deal with moles, then we're dealing with quantities that we can actually see. Yeah?
Is it like writing the equations but just not in the simplest form or simplest version?
Well, it's like changing the unit is really what it's like. So that would give us 2 moles of the carbon dioxide. Trying to think, because you guys are having good questions, and this is an idea that's really important to get your head around. Okay, so how about hundreds? If I had 200 carbon monoxide molecules, how many oxygen molecules would I need? 100. And how many carbon dioxide molecules would I get? I'd get 200. What if I had 2 million of these? It would react with 1 million of those to make 2 million of these. So it has to do with numbers of particles, but we can change the unit, if you will. We can do millions, billions, trillions, but what chemists choose to do is we use mole. Okay, so any chemical reaction, basically what we're doing is we're taking this and I'm just going to get rid of this. We're inserting mole, the unit mole. 2 moles of this, 1 mole of that, 2 moles of that. That's the most common way that we interpret chemical equations. Any other questions? When we use that mole interpretation, we can write what are called mole ratios from the balanced chemical equation. And this gives us the relationship of the quantities between the different reactants and products. So if we look at this, we can interpret this as 2 moles of CO. So 2 moles of CO will react with 1 mole of O2. Or I could say that I will get 2 moles of CO2 for every 2 moles of CO that react. What we're doing, here's an understood 1, and then we stick the unit mole in here. we can take any two reactants and or products. They could both be reactants, they could both be products, could be one of each, and we can make a conversion factor directly from the balanced chemical equation. So then we can answer questions like this. How many moles of oxygen will react with 2.5 moles of carbon monoxide? I mean, it's easy to answer how many moles will react with 2 moles because that's the number in the equation. But what if it's 2.5? Well, we're going to use dimensional analysis here. We've got 2.5 moles of carbon monoxide. And we want to know how many moles of oxygen. So the unit we want is moles of oxygen. And we want to get rid of this unit, moles of carbon monoxide. The relationship between moles of oxygen and moles of carbon monoxide is in the chemical equation. 2 moles of carbon monoxide to 1 mole of oxygen. And so what do I end up with here? I have 1.25 moles of oxygen. Does that make sense? It makes sense to me, but I've been doing this for years, so I need to know if that makes sense to you. The balanced chemical equation gives us relationships in terms of numbers of particles, and mole is a number of particles unit, between the different reactants and products. Let's do one more. What am I trying to do here? I don't even know what I'm trying to do. I'm going to make up another question. So how many moles of carbon dioxide are produced from 17 moles of oxygen? Well, we've got 17 moles of oxygen reacting, and we want to know how many moles of carbon dioxide are produced. This is our starting unit and number, and moles of CO2 are what we're trying to get to. So if we're going to go back to the basics of dimensional analysis, we figure out what we're trying to find out. So we're trying to find out moles of CO2. And then we have to identify what are we starting with. We're starting with moles of oxygen. And these mole-to-mole conversions are always one step. So 17 moles of oxygen. And then I want moles of CO2 on the top and moles of oxygen on the bottom. Always put the units in first and then put the numbers in. What's the relationship between moles of CO2 and moles of oxygen? Well, we're talking about this particular chemical reaction, and for every 1 mole of oxygen, we produce 2 moles of CO2. So 2 moles of CO2 per 1 mole of oxygen. And then we do the math, and we get 34 moles of carbon dioxide. Any questions? This is a simple equation, and I'm using simple numbers so that you can probably see how it works, but then also look at the mechanics of the dimensional analysis. You might be able to say, well, yeah, obviously I just need to multiply it by 2 and I'll get the answer. But what if this is 3 and that's 7? Then it's not as clear. And then we're going to add some things on the ends of this and get into grams. So it's very important to understand the mole part. So let's do an example here. That's kind of a scary looking example, isn't it? There's all these words. There's a lot of black stuff on that slide. Urea, and it gives us the chemical formula there, is a byproduct of protein metabolism. This waste product is formed in the liver and then filtered from the blood and excreted in the urine by the kidneys. Urea can be synthesized in the laboratory by the combination of ammonia and carbon dioxide according to the equation. Okay, that's all really nice and everything. That's just kind of backstory. They're trying to pump some information into your brain on the sly in these problems. Do we need to know all that to solve the problem? No, we just need the balanced chemical equation. So here's the actual question or statement. Calculate the amount of urea that will be produced by the complete reaction of 5.25 moles of ammonia. Well, it doesn't say amount in what unit. I'm going to add in here, amount of urea in moles. These sorts of calculations, this is called stoichiometry, by the way. I don't think, have we used that word yet? Stoichiometry? Okay. It's mentioned in a title, yeah. Stoichiometry, I don't think I defined it in the slides anywhere. Stoichiometry is looking at the relationships of amounts of reactants and products in a chemical reaction. It's very useful. Because you go out and, you're in industry and maybe you're trying to make fertilizer, right? The fertilizer is made by a chemical reaction. And you want to know, well, how many pounds or kilograms of starting ingredients do I need to make this much fertilizer? It's a very practical kind of question. How do you figure it out? You use stoichiometry. So that's what we're studying today. So we've got this balanced chemical equation and we've got this problem here. I like to use the balanced chemical equation to help me organize the information that's provided in the problem. So where it says 5.25 moles of ammonia, I'm going to write that under the equation. Which one of these compounds is ammonia?
NH3.
The NH3. We should know that. Ammonia is one that you're supposed to memorize. So here's the ammonia, and I'm given an amount in moles. I'm just going to write 5.25 moles right under there. And then what are we trying to find? The amount of urea. Okay, so they did give us the formula up here. If they didn't give us the formula, we could figure out which one of these it is by process of elimination. We know that this is water, and that's carbon dioxide, and this is ammonia. So this other funny-looking one must be the urea. This is what we're trying to find, question mark, and I added in there, we're looking for moles. So now we've clearly identified where we're starting and where we're ending. We're starting with this many moles of ammonia, and we're trying to find the moles of urea. That's a one-step process. So the path over here, I'll just squeeze it in right here. We're going to go from moles of NH3 to moles of urea, NH2 to CO. That path tells me exactly what to do in the calculation. 5.25 moles of ammonia. And I'm going to have one fraction. I want moles of urea on top. Yes, it gets a little tedious sometimes writing all these chemical formulas. Just do it anyway. Moles of ammonia cancel out. The numbers for this conversion factor are the coefficients in the balanced chemical equation. It is that simple. You don't have to go anywhere else. I'm going to find ammonia, NH3. What is the number in front of it? It's a 2. So in this equation, in my conversion factor, I write a 2 in front of NH3. I also need the number of moles of urea. What number is implied in front of the formula here? A 1. So that's a 1. There's no trying to figure out, am I supposed to multiply by 2 or divide by 2? Just let the units tell you what to do. And so then, I should do that. I should be able to do that in my head, but I know I'll screw it up. 2.625. Yeah, I would have messed that up. 2.625 moles of urea is what the calculator gives us. How many significant figures should that have? 3. It should have 3 because of our starting number of significant figures, and so we would round that to 2.63 moles. These numbers are exact numbers because they come from 2 molecules of ammonia reacting with 1 molecule of CO2 to produce 1 molecule of this and 1 molecule of that. It goes down to individual particles interacting, and those are exact numbers. Any questions? Let's do another one here. It says, determine the stoichiometric amount of carbon dioxide required to react with 5.25 moles of ammonia. The stoichiometric amount means, using stoichiometry, find out how much of it is needed to completely react. And so it's the same type of calculation, they're just using fancy words. So again, I have 5.25 moles of ammonia. Now they're asking me about the carbon dioxide. So I'm going to get rid of the other question. Now my question is, how many moles of carbon dioxide? So now my path is moles of ammonia to moles of CO2. So 5.25 moles of ammonia. My path tells me what to put on the top, moles of CO2. And then I want to put moles of ammonia in the denominator so that those units cancel out. What number should I put in front of moles of CO2? 1. Because up here in the formula, it's talking about 1 mole of CO2. What number goes in front of the moles of ammonia? 2, because it's 2 moles. 2 moles of ammonia react with 1 mole of CO2. And so this ends up being the same number, 2.63 moles of CO2. Any questions? If I look at this equation, these answers should make sense. It should take the same number of moles of CO2 to react with that amount of ammonia as the number of moles of this that are produced. Because this says for every 2 molecules of ammonia, I'm going to use up 1 molecule of CO2 and I'm going to produce 1 molecule. So in terms of counting particles, it's the same number. So the chemical equations give us relationships of moles, but we don't actually measure things in terms of moles because mole is a counting number. We measure them by weighing them. We use a balance, and we measure the mass in grams or kilograms, and that's how we identify how much starting material we have, how much product was made. So we're still going to use this mole to mole, but now we also have to add a little thing onto the front of that calculation and a little thing onto the end. So a more practical problem is, well, if I had, 25 grams of ammonia, how many grams of CO2 would I need to react with that? And so you would take the mass of your starting thing, you'd convert it to moles. We've learned how to do that. You use the molar mass of the substance. And then you go from moles of that one to the moles of the one you're interested in, and then to grams of that, again using the molar mass. This part in the middle, the mole to mole, is always part of stoichiometry. The ends can change. We're only going to talk about mass problems in this class, but there's all kinds of other variations that you'll get into in Chem 1A. But if you have the mass to mass one down pat, then just changing it up a little won't be a problem. So this is nice, mass to moles to mass, but I don't know. I like grams to moles to grams better. Same idea. This is like the stoichiometry chant. It's the path for all of these types of problems. Grams to moles to grams. Grams to moles to grams. And you know that you're getting it when you wake up in the middle of the night muttering, grams to moles to grams, right? Then it's really getting into your head. This is the path for all of them, okay? It's great, one path. So let's do an example. Calculate the mass of iron filings required to produce 0.455 grams of silver metal given the unbalanced equation for the reaction. So we're going to get a little practice in balancing equations here. You have to use a balanced chemical equation to do these calculations. What do we need to do to balance this? If we just, start looking at it, we've got one iron here and one iron there and one silver, and we're like, well, what's the problem? The problem is the nitrates, isn't it? Here's one NO3, one nitrate ion, and over here, there's 3 of them. So how can I fix that? Somebody.
Oh, you put a 3 in front of silver nitrate.
Yeah, let's put a 3 here, and then a 3 over here. Everybody okay with that? So there's our balanced chemical equation. Let's go back to the problem. Calculate the mass of iron filings. Iron, that's this guy. That's what they're asking us to find. Calculate the mass. So under iron, I'm going to write question mark grams. It didn't specify the unit. If it doesn't specify the unit, pick the easiest one. And then it says 0.455 grams of silver. Well, Ag is the silver, right? So they're telling us 0.455 grams of silver. So this is not moles of one to moles of the other. It's grams of one to grams of the other. So what's the stoichiometry chant? Grams to moles to moles to grams. So this is the one with the number, so this is where we're starting. We're going to go grams of this to moles of this, to moles of that, to grams of that. So we've got grams of silver to moles of silver to moles of iron to grams of iron. Everybody okay with that? Gram to mole conversions, we've been doing for a couple of days now. We use the molar mass, right? So that's fine. We can look the molar mass of silver up on the periodic table. And here we have another mole gram conversion, again, molar mass from the periodic table. The one in the middle, this conversion here is what we just learned how to do. And that's using the coefficients from the balanced chemical equation. For every 1 mole of iron, we're going to get 3 moles of silver. So once we have the path, then you just follow the pattern. 0.455 grams of silver. There are 3 fractions because there are 3 arrows. These are the units that go in the numerator. Grams of silver, moles of iron, grams of iron. So I've already got grams of silver. We have moles of silver and moles of iron and grams of iron. And then I put the unit from the previous term in the denominator because I want those to cancel out. I don't want to end up with grams of silver in my final answer. Grams of silver will cancel. And then I'm going to put moles of silver down here. And moles of iron down here. So the units cancel out. After we fix up the units, then we go looking for numbers. I think this one in the middle is always the easiest because it's just picking numbers out of the balanced chemical equation. In front of the Fe is an unwritten 1. So in front of moles of Fe, I'm going to write 1. In front of silver is the number 3. So in front of moles of silver, I'm just going to write the number 3. That's the ratio in which silver and iron interact in this equation. Over here, for silver, I just need to look silver up on the periodic table, 107.9. 1 mole weighs 107.9 grams. And then over here, I need the mass of iron, 55.85. 55.85 goes with the unit gram. That's the mass of 1 mole. Molar masses are always the mass of 1 mole. So the number goes with grams, and 1 goes with mole. And now we just go across, multiplying and dividing, and get an answer. 0.45 divided by 107.9 divided by 3 times 55.85. And as often happens, my calculator gives me a mess. 0.078504016. And what's the unit on that? Grams of silver. It's the only one I didn't cross out. All the others canceled out. Grams of silver. How many significant figures should that answer have? Sorry, grams of iron, yes. Grams of iron. Our starting mass had 3 significant figures. The molar masses we used had 4, and this mole ratio is exact. So the starting number is limiting. Remember, these leading zeros don't count as significant figures. So it's the 7, the 8, and the 5 that we're keeping. The next digit is less than 5, so we round down. 0.0785 grams of iron. Any questions? Let's do the scary example from the book. Nitrous oxide, N2O, also known as laughing gas. What's another name for that? N2O. How did we learn to name it? Dinitrogen monoxide. It's commonly used as an anesthetic in dentistry. It's manufactured by heating ammonium nitrate. The balanced equation is given here. Calculate the mass of ammonium nitrate that must be heated in order to produce 10.0 grams of nitrous oxide. So we read through the problem, and we're looking for the question or the request, and we're looking for amounts that are given. So the question or request is calculate the mass of ammonium nitrate. So I'm going to use the chemical equation here to organize myself. I'm looking for question mark, grams. And it's how much of that to produce 10 grams of nitrous oxide. So I want to make 10.0 grams of nitrous oxide. How much ammonium nitrate do I need to start with? We're given a mass, we're asked for a mass. You can't go directly from the mass of one to the mass of the other. You have to go through moles. Grams to moles to moles to grams. So our path is going to be grams of N2O to moles of N2O. Until this really clicks in your mind, I want you to write this path out. Once you get good at it, you'll be able to skip that and just go to writing down the equation. But don't start out that way. Moles of N2O, and then I'm going to go to moles of the thing I'm looking for. Moles of NH4NO3. And then to grams. I ran out of room. NH4NO3. So I've got the path written out. That just tells me exactly what to do now. So we're starting here with 10.0 grams of N2O. I'm going to have 3 factors. Grams of N2O to moles of N2O to moles of ammonium nitrate to grams of ammonium nitrate. And then put the other units in so they cancel out. Units in place, then I look for numbers. I like to do the middle one first because it's easy. So I look at the balanced chemical equation. There's a 1 implied in front of ammonium nitrate. So I'm going to write a 1 in my ratio here. And the N2O also has a 1. You may think, well, why do I need to write that down? Because a lot of times it isn't 1-to-1. And you need to be able to show your work with all the units. Even if you get to the point where you can do a calculation like this in your head, you need the ability to write it down clearly. Then we need molar masses, don't we? So we need the molar mass of N2O. So that would be 2 times the mass of nitrogen plus the mass of oxygen (44.02). So that means that 1 mole of N2O weighs 44.02 grams. And then I need the molar mass of ammonium nitrate. In ammonium nitrate, here it is, there are 2 nitrogens, 4 hydrogens, and 3 oxygens. So 2 nitrogens, 4 hydrogens, and 3 oxygens. I'm getting 80.052. One mole of ammonium nitrate weighs 80.052 grams. So now just go left to right, multiply by the top, divide by the bottom. So 10, you can do times 1 if you want to, divided by 44.02, times 1 divided by 1, times 80.052 divided by 1, and my calculator gives me this number. How many significant figures should that have? 3. We're starting with 3 here. Our molar masses each had 4, and then this is exact. You would like to use molar masses that are not going to reduce the number of significant figures in your answer. That's usually not a problem in questions that are set up for you like this. So we'll round that to 18.2 grams of ammonium nitrate. Any questions? How much water would be produced along with that? Well, that's a different question, isn't it? So now they're asking us, what mass of water? Well, again, we've just got this information here, the mass of N2O. But now our path will be grams of this to moles of this to moles of water to grams of water. Grams of N2O to moles of N2O to moles of water to grams of water. Very, very similar calculation. 10.0 grams of N2O times, I want to go to moles of N2O, and then I'm going to go to moles of H2O, and then grams of H2O. And again, I'm going to fill these units in the denominator to cancel out the previous term. Well, we don't have to calculate the mass of N2O again, because we already did that, and that hasn't changed since 5 minutes ago. So it's still 44.02. So 44.02, 1 mole of N2O. What about this mole ratio? It's going to be 2 to 1 this time, because there's 2 moles of H2O. There's a 2 up here. So this 2 needs to come in here. 2 moles of H2O for every 1 mole of N2O. And then we need the molar mass of water. We've done that a bunch of times. It's 18.016. So 10 divided by 44.02 times 2 times 18.016 equals blah, blah, blah. How many sig figs should this one have? 3 again. So 8.19 grams of water. Any questions? This is like one of the bread and butter calculations in chemistry.
I have one question. When you look at the mole-to-mole ratio, I see the 2H2O and then the 1N2O. Where are you? You have to pay attention to both sides, depending on what it's asking, right?
Right.
Depending on what the question is asking. And in this case, it's asking us how much of the N2O, the nitrous oxide grams, which is what we're starting with, that's on this side of the question. And
Right.
we're paying attention. So that we looked at over here.
So in the first one, we were looking at the ammonium nitrate and the N2O. And in the second problem, we're looking at 2 of the products. And so we've got the N2O and the H2O. And so for this mole ratio, we just go to the formula that's in the ratio. So moles of H2O, I find H2O wherever it is, reactant or product, and I ask myself, what's the coefficient in front of it? That's the number that goes in the ratio. And here, moles of N2O. Well, I find N2O in the balanced chemical equation. What's the coefficient? Well, there is no coefficient because chemists don't like to write the number 1. So I understand that it's a 1. Does that help? It doesn't have to be, I'm given an amount of reactant, I'm going to find an amount of product. It can be 2 reactants, it can be 2 products, it can be given the amount of product, find the reactant. Any combination of things in the balanced chemical equation. Any other questions? Yeah.
Would it have been all right for Part B if we started with the grams that we got for ammonium nitrate rather than N2O?
Yeah. In doing this question after this one, you could take the mass of ammonium nitrate and do a very similar calculation and come up with a mass of water from that, and you should get the same answer. Yeah. And, you know, some of you may see some shortcuts or something that you could do in here. There are shortcuts, there are other ways of doing it, but I find that students you just need to learn the pattern. I like this because it always works, and I think that's awesome, right? And once you get comfortable with that, if you come up with some shorter ways to do some things, that's fine, as long as you understand the way to write the whole thing out.